We've talked a little bit about conditional probability and how we find conditional probabilities, but now we're going to talk about something related to that. So we say that two events are independent if one happening doesn't actually impact the probability of the other happening. So let's say I'm looking for the probability of A given B. If the events A and B are independent, then it actually doesn't matter that we have that extra information that B happened. This conditional probability will be equal to the probability of A. And we say that events are dependent if one happening does impact the probability of the other happening. And so there's an example here where you can try different versions of problems where you can calculate probabilities and decide if the events are independent or not. But I want to try this exercise 3 here, and in this one we'll try to see if some events are independent. So in exercise 3, it says a delivery service operates in a city where it snows in the winter. And now it's the winter, and we're going to look at the events that on a randomly selected day that the delivery service is late making deliveries, and the event that it snows that day. So we have these two events, they're late and it snows. And it says, suppose the probability that service is late on this day is 0.17, and the probability that service is late given that it snows is 0.7. And the probability that it snows is 0.18. So we have these different probabilities. Let's see, the probability that they're late making deliveries, I'm just going to write down what they've told us, is 0.17. The probability that they're late given that it snows, if we already know that it snows, then it's way more likely that they'll be late. And the probability just in general that it snows is 0.18. So right away, we actually know that the events, it being late and that it snows, we actually know that those are dependent. And that's just from the information that they've given us. If we just look at these first two probabilities, those two probabilities are not equal, which means that these events are dependent. Because to be independent, we would need this extra information about it snowing not to affect the probability that they would be late, but these numbers here are not equal, and so these events are dependent. They are not independent events. And so this part C here asks, are the events the service is late and it snows on this day independent? No, we already know the answer to that because the probability that they're late and the probability that they're late given that it snows are not equal, and so these events are dependent. But now let's try to find these other probabilities in this problem. So part A says find the probability that the service is late and it snows on this day. So let's see, part A, the and means we want to find the probability of the intersection. We want it to be late and snow on the same day. So that intersection is like an and. So this is the probability that we want to find. And in the last section, we had a formula for conditional probabilities that involved intersections, and that's what we want to use here. So using our formula, I'm just going to kind of do some scratch work off to the side. If I wanted, let's see, we know the probability that it's late given that it snows. We already know that, they gave it to us. But if we wanted to find this, we could use that formula for conditional probabilities that we learned earlier. So using our formula for conditional probabilities, we would say that this probability is equal to the intersection, the probability of the intersection, so late and snows, divided by the probability of the thing we're given. So divided by the probability that it snows. Well, in our problem, they gave us the probability that it snows, and they gave us this conditional probability, and we want to find the probability of the intersection. So we could solve this formula, this equation, for the probability of the intersection, which is what we want to find, and we would do that by multiplying both sides by the denominator. So we would multiply both sides by the probability that it snows. And then if we solve for, or let's see, these would cancel, and on one side we would be left with the probability of the intersection, and on the other side we would have the conditional probability that we started with times the probability that it snows. So I know I've switched the left and the right sides here, but this tells us just in general that the probability of an intersection is equal to the probability of A given B times the probability of B. So this is true in general. And using our formula, now we can plug in the numbers that we were given in the problem. So the probability that it's late and snows is equal to the conditional probability, which is 0.7, times the probability that it snows, which in the problem said was 0.18. So if we plug those into Excel or a calculator and multiply these two things together, we'll get that this is 0.126. And so this probability of the intersection is about 12.6%. Okay, great. So this was part A. We found the probability that it's late and snows. Let's see, part B said find the probability that it snows given that the service is late. So now we want to find the probability that it snows given that they're late. So this is a little bit different than finding the probability that they're late given that it snows. Now we're saying we already know that they're late. What's the probability that it snowed on that day if we already know that they were late? So here we can use our conditional probability formula and say this is the probability that it snows and they're late divided by the probability of what we were given, which was that they were late. Well, it turns out that if I'm finding the probability of an intersection, it doesn't matter the order. So I could have switched the order of these, the snows and the late part, in that situation, and we already know the probability of that intersection. We found it in part A. So that intersection probability is 0.126. And the probability that they were late, they gave us in the problem, that was 0.17. So this probability we're looking for is 0.126 divided by 0.17, and this is about, if we round, this is about 0.74. And we could round a little bit farther. We could show more decimal places if we wanted to, but this is that probability. So if we know that they're late, there's about a 74% chance that it snowed that day. And if we wanted to revisit the question of if these events are independent or not, let's see, here's another way of seeing that they are not independent events, because this probability that it snows given that they were late, that does not equal the probability just that it snows, because the probability that it snows was 0.18, and that's not equal to 0.74. And so this is just another way to see that these are not independent events. And there are some situations where knowing if the events are independent or not can actually make it easier to calculate probabilities of intersections. So the multiplication rule for probabilities is used to calculate the probabilities of intersections, and for dependent events, it's this formula right here. And this we actually solved for given our conditional probability formula. When we multiplied both sides by the probability of B, this is the formula that we got, and we used this in the last problem. So this formula that we figured out in the last problem was that in general, the probability of an intersection is the probability of B times the probability of A given B. That's something we figured out using our formula for this conditional probability. Well, if our events are independent, so if A and B are independent events, then this conditional probability, knowing B doesn't change this probability, and that probability is just the probability of A. So our formula really becomes that the probability of the intersection is the probability of B times just the probability of A. And this is really convenient, and I'm going to write this just in the other order so that we can see this. If my events are independent, then to find a probability of an intersection, I just find the probability of each event and multiply them together. And if I have more events, I can still just keep multiplying the probability of each one times the other, if my events are independent. And so this makes it much easier to find the probability of intersections if our events are independent. So let's look at exercise 4 here and see how we would use the formula if our events maybe are not independent. And then in the next exercise, we'll see how easy this becomes if they are independent. So in exercise 4, it says a company has 140 employees, of which 30 are supervisors. And 80 of the employees are married, and 20% of the married employees are supervisors. And if a company employee is randomly selected, we want to know the probability that that employee is married and is a supervisor. So that and means we want to find the probability that they're married. I'm going to just use M for the event that they're married. And means intersection, the event that they're a supervisor. And I'm going to use S for supervisor. So I want the probability of this intersection. They don't tell us anything about these events being independent, so I'm going to assume they're dependent and use this general formula. So this would be, let's see, there are 2 different ways we could write this, depending on which is A and which is B. So maybe I should pause for a minute. This formula has a conditional probability. Let's see what we are given. We are given that 80 of the employees are married and 20% of the married employees are supervisors. So that statement right here is telling us that if we look at the probability of being a supervisor, if we're given that they're married, that probability is 20% or 0.2. So since that's what we're given, I'm going to rearrange our intersection just to copy the formula a little bit better. Remember that I can switch the order of my events when I'm taking an intersection. And now if I write this formula this way, I would have that this is the probability of M times the probability of S given M. And I did it this order instead of, the other thing I could have done is say that this is the probability of S times the probability of M given S. That would have been correct, but I wouldn't have known this conditional probability, and that's why I chose the one that I did. Because if I want to now find the probability that they're married, I would say, well, 80 of my 140 employees are married, so the probability that one of them is married is 80 over 140, and then the probability that they're a supervisor given that they're married is that 0.2. And so now if I do, let's see, 80 over 140 times 0.2, that will end up being, if I plug this into my calculator or Excel, this will be about 0.114. And so this tells us that if I just randomly select an employee, then the probability that they're both married and a supervisor is about 11.4%. And I could use this formula right here. I just had to figure out which event I should have be A and which I should have be B. So now let's look at exercise 5 and see how much easier this becomes if I have events that I can assume are independent. So this exercise says, suppose that 70% of people own dogs. If I pick 2 people at random, what's the probability that they both own a dog? Well, now we have to think for a second. Do you think if one person owning a dog should affect the probability that another person owns a dog? I'm going to assume not. I'm going to assume that these events are independent, that one person owning a dog doesn't impact the probability that someone else owns a dog. So this assumption might not be quite right in certain situations, but in general, it doesn't seem like me owning a dog should impact whether or not you own a dog. And so just 2 random people, I'm going to assume that these are independent events. So the probability that one person owns a dog is 0.7. And if these are independent events, I can just multiply that by another 0.7 for the probability that the other person owns a dog. So this would end up being 0.7 squared. So 0.7 squared, in Excel, you could type in 0.7 and then the little caret if you did shift 6 and then put a squared. This would find the probability that, this would find 0.7 squared, and this would be 0.49. So if I choose 2 people at random, there would be about a 49% chance that they both own a dog. What if I wanted to find the probability that 3 random people, so 3 randomly selected people, own a dog? Well, I would still assume that these are independent events, and I would do 0.7 times 0.7 3 times because I would have 3 people. And this is really convenient when we have independent events. We don't really have to use that formula above. We just multiply our probabilities together. And this would be about 34%. And so independent events are really nice, and they make finding probabilities much easier. And so in general, the formula that we want to use is this one right here. But if our events are independent, we can just multiply the probabilities together.